Hello. We are going to do a bunch of mini lectures today to finish up chapter 2. I'm going to try to keep them pretty short and minimal so you can have the lecture slides and the book to supplement everything. And then you do have a class exercise, which is totally optional. You guys won't be doing it at the same time, but those are kind of fun exercises. Those are never graded in class either. They're just kind of bring this alive a little bit more. I think we did most of the class exercises for this chapter already. There might be a couple more. And then there is an ICLA that you do have that will be due by the end of today, Wednesday. And you'll submit that in D2L just like you do with your, with your weather forecast discussion. That is also in D2L. You're going to do it you're going to download it the same way you did for the weather forecast discussion and then submit it. If you have trouble submitting any of your work from this, and I am not here to help you troubleshoot, don't worry. Just send me a message and let me know that the work is done, but you weren't able to submit it in D2L. I will not mark you off for it, and then we'll do it. We'll work together to figure out D2L when I get back. Okay, so let's dive right into chapter 2. Now we're going to switch gears and talk about radiant energy. So radiant energy is the energy that comes from the sun. We're going to dive a little bit deeper. The way that we evaluate radiant energy is through wavelength. Remember we talked about electromagnetic or radiant energy comes in waves. And what we do is we look at the wavelength, and the wavelength is the distance between the two peaks. When the waves are further apart, the wavelength is long. When they're closer together, the wavelength is short. So on this graph here, we can see that X-rays have a very short wavelength, and these are measured in microns. So this is a graphical representation that's blown the waves way, way up. I mean, these are microns, so that's very, 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 very small, like microscopic. So even here, actually, this says it's in meters. So an X-ray's wavelength is 10 to the minus 9 meters. So it's very tiny. So generally, we talk about waves in a couple ways. Shorter wavelengths means that the peaks are closer together, and that can be going from this, like going anywhere downwards on this, or our wavelengths are longer, like comparative, and we're going upwards on this this graphic. But we also have it designated for short wavelengths and long wavelengths, and we will get to that. So here we have, we're talking about how these shorter, when you have electromagnetic waves, the shorter the wavelength, the more energy it has, because that's what we're talking about in this chapter, all of the energy. So when we're looking at this graphic again, AM radio waves have the longest wavelength for the things that are plotted here, so they would have the least amount of energy. And as we go down to the bottom, ultraviolet waves, which we talk about, UV waves, that's why you put UV radiation, that's why you put sunscreen on. Those are really short wavelengths. They're really close together. And then more than that is X-rays. Here we also have visible light, which is relatively short. Like there's pretty short wavelengths. Then we have infrared, which should sound familiar. That's one of the satellite images that we look at. We'll talk about that a little bit more later. Okay, here's your first ICLA. Go ahead and pause it and do this. Like I said, if you have contact information for your lab mates, go ahead and contact them. You guys can do it together. You can do it on your own. Everybody's going to be turning in their own. But you can still work together. So pause it and go ahead. And then I'm just going to continue, which feels a little weird. Okay, radiant energy. Everything that has a temperature above absolute zero, that means 0 Kelvin, not 0 Celsius, emits radiation. That means that the wall behind me is emitting radiation. I'm emitting radiation. This awesome microphone is emitting radiation. My cold glass of water is emitting radiation. And the sun gives off a lot, a lot. So how do we know that? There are 2 physics laws that we're going to dive into. They may look a little tricky, but don't worry. I got tricks. I got tricks too. First, we're going to look at the Stefan-Boltzman law. And basically, this says the higher the temperature of an object, the more radiation is emitted each second. Okay, so the equation is this. It's actually really simple. E is for emittance of total radiation from an object, and T is temperature to the fourth power. So you multiply it by itself 4 times, and then we have a constant, which doesn't change. So when we think about something like my temperature, we'd have to convert it to Kelvin, which I'm not good at conversions, compared to the sun, which the sun is 6,000 degrees Kelvin. I'm definitely way less than that. If we were to put into this equation, we would see that the sun emits so much more energy than I do. But we can calculate how much energy these things emit. Okay, so this equation tells us something about the amount of energy being emitted, and it's solely dependent on the temperature of an object. So here is your first class exercise. You'll be doing this alone, but maybe you'll go in there and somebody else has already done something, because this is still a document that you guys are all working on together. You have 5 pictures here. You are going to rank them from 1 to 5 about which object do you think is emitting the most radiation? That should be 1. And which is emitting the least radiation? That is 2. In this image, you're classifying the tree. Here, you're classifying the meteorologist. You might know who he is. Here, you're just the atmosphere. This is supposed to be the sun. It's not a picture of the sun, and this is a hot pot. Okay, pause it, do that, and come back. And now I'm going to tell you, you just did this. You just did this equation. It is actually that simple. If you have an idea about the temperature of you didn't give us a number, but you have an idea about how much energy things emit based on their temperature. So now you're going to go around just looking at everything being like, oh my gosh, that's so much energy. Oh my gosh, that's not a lot of energy. Or at least your teacher can hope, right? Okay, so the next physics law we're going to talk about is called Wien's law. And this is used to determine the wavelength. So we're talking about wavelength again, at which the most radiation occurs from an object. Okay, it's a little bit trickier. We have these plots that we're going to look at a bunch of them. And down here on this axis is the wavelength. And here is how much the radiation intensity. So that's like how much energy is being emitted. And then an object like this is for the sun, emits radiation over a spectrum, but there's a point because of the temperature where it emits most of it, and it emits most of it at certain wavelengths. Okay, so what this white line is, it's telling us the different wavelengths that the sun emits at, and where we have the most, that's where the sun emits most of the radiation. That's what this equation is telling us. Lambda is a wavelength. Okay, its units are going to be in microns. We have a constant, and it's divided by temperature in Kelvin. So again, in order to determine the max wavelength something emits at, where most of its energy, that's the wavelength that it's emitting at, all it's based on, again, is temperature. It's a really easy equation. It may look complicated when we're looking at this plot, but it's not that complicated. So let's break it down a little bit more. So we have 2 plots that are very similar. Again, wavelength. The wavelengths here are 0.4 to 0.7 microns. That's the ones that are labeled. Again, radiant intensity. Then we have over here, this is for the sun, this is for the earth. Okay, so we have a much smaller peak. Why is that? Right? Because the earth is much colder than the sun. Thank goodness, or we wouldn't be here. Then on here, we have wavelength in microns. Now look at, these are 0.4 to 0.7 microns. This plot starts at 0.5. So we already know that the Earth's wavelengths are longer than the wavelengths that the sun emits at. So the way that we look at this equation, the Earth or the sun is about 6,000 Kelvin degrees, very, very hot. The Earth is about 288 degrees Kelvin. So Wien law tells us that the sun gives off energy mostly as shortwave radiation. The higher the temperature, the shorter the wavelength, because they're giving off more energy. We saw that in our plot, like right when we started. And this plot actually shows us as well. So we can see that where the white line is the highest, that's where the sun emits, that's the wavelength that the sun emits most of its energy at. If we were to pick one wavelength, it's about 0.5, but you can see that most of the wavelengths that the Earth emits at, or the sun emits at, sorry, I think I just said Earth, the sun emits at are from 0.4 to 0.7 microns, and that's the visible spectrum. Okay, here we have the Earth. Its maximum wavelength that it emits at is where this is at a peak, and it's about at 10. This is where we find that cutoff for shortwave and longwave radiation. So the sun mostly gives off shortwave radiation. That's where its peak is, and the Earth mostly gives off longwave radiation. So when we have designations for short and long wave radiation, not when we're just comparing, shortwave radiation is basically anything that has a wavelength shorter than 1 micron, and long wave radiation is anything that has a wavelength longer than 1 micron. So that's another way you can look at this. Again, the sun emits mostly in the visible spectrum. That's actually why our eyes have evolved to see visible light. And that's from 0.4 to 0.7 microns. Each of those colors, and then we have on here the spectrum of colors. Each color has a different wavelength. The shortest wavelength is purple, and the longest wavelength is red. That will come into play definitely when we start talking about rainbows and optical phenomena, but just something to tuck away. But also note that even though that's the peak of radiation, the sun gives off a ton of radiation in the ultraviolet. And ultraviolet is extremely high energy shortwave radiation. That's what gets absorbed in the ozone layer. And thank goodness, because if it didn't, it'd come down and it'd be absorbed by us or the surface, like we talked about yesterday or on Monday, and we'd be some crispy critters. We also see that in this spectrum that the sun still does radiate at longer wavelengths. So it's a spectrum of how the wavelengths it emits at, but it mostly emits in the visible spectrum. Okay, so now we have another class exercise. What emits more energy, the Earth or the sun? And then you have a class activity where you are going to look at these two graphs and answer some questions. So that's where I'm going to end this video, and I will see you guys in a few minutes for your next video.